So for stresses in saturated soil with seepage, if the water is seeping, the effective stress at any point in a soil mass will be different from the static case. It will increase or decrease depending on the direction of the seepage. So right here we will have uh, inflow or outflow of water underneath the surface of the soil layer. So it's either upward or downward direction. So that may increase or decrease the effective stress at any point on the soil. So how do we solve the stresses in saturated soil with upward seepage? The stresses at point B, or the bottom portion of the soil layer. So we can use again the solution for the total stress equals to the sum of the effective stress and the pore water pressure. So if we are to determine the effective stress, just take the difference of the total stress and the pore water pressure. So it's just the same, but for saturated soils with upward seepage, here's what makes the difference. So if the saturated soil is in the static state, so we can use again the same solution where we just multiply the unit weight of water to the total height from the water surface or the water table to the point where we will determine the total pore water pressure, which is at point B. So H1 plus H2. So in upward seepage, we will have an additional pore water pressure here. So based on what you see in the figure, so the tendency of the pore water pressure above point B is to have a downward direction of the pore water pressure due to gravity. But on the other hand, we have an upward seepage. So if we have an upward seepage, it means that at point B, okay, at point B, we have two pore pressure that is directing towards point B. So it means their pressures will combine or they will add. So the total pore water pressure will increase. So this will be your additional pore water pressure. It's just the product of the unit weight of water to H. So what's H here? So the H here is if we have the piezometers placed at each level of the soil layer. So from top to bottom or at the middle. So if we take the difference of the pressure head from top, which is at point A, to the bottom, which is point B, so that would be your H there. So the difference in pressure head when you put a piezometer at each point. So the H here is multiplied by the unit weight of water. So since we have the same unit weight of water, that we will multiply to the heights. So we can just factor out unit weight of water and add all these heights. So H1 is H2 and the H. So at stress at C, which is an intermediate point between the soil layer. So we have the same solution, only that if we are going to determine the pressure head difference from the top, okay, from the top surface of the water to the point to the pressure head of point C. So here's the equivalent height. We have a solution of H over H2 times Z. So where did that come from? So we just take the ratio of the pressure head difference between point A to B and point A to C. So the ratio of pressure head difference with respect to its depth. So let's say considering point A to point B. So the pressure head difference is H, and the depth is H2. So we equate that to the pressure head difference, let's say Hz for point A and point C. So Hz over the depth, which is Z. So we multiply both sides by Z to eliminate Z here, and we're able to determine the equivalent pressure head difference of point C and point A. So we have H over H2 multiplied by Z. So that's your equivalent pressure head difference. So just multiply it again to unit weight of water and add that to the initial pore water pressure. So that's it. The main difference is that we have an additional pore water pressure due to the upward seepage. Okay, so we can combine the three heights. We add the three, and we're now able to determine the pore water pressure. So for stresses in saturated soil with downward seepage, so as you can see in the figure, the pressure head at point B, or the bottom portion of the soil layer, is that the pressure head is lower than the pressure head at the top portion of the soil layer. So it is an implication that there is a decrease in pressure at point B. So the main difference for uh, this solution is that for computing the pore water pressure, so that additional pore water pressure there that we will add is that we use negative sign. So, okay, we use this. This is negative right here. So same applies. Same solution applies with the upward seepage to the downward seepage. So they only differ in the sign of that addition of that pore water pressure that we will include due to the seepage. Okay, so this is negative sign, but same solution applies. So H is the difference in pressure head for A to B, and uh, Z is the depth at point C, H2 total depth of soil. So same solution, negative and sign. Next, for the seepage force, here are the formulas. So the seepage force can be determined by multiplying the unit weight of water to H over H2. So H over H2 is just the ratio of the difference in that's the difference in pressure head over the total depth of the soil. So we can also rewrite that as I times unit weight of water, where I is the hydraulic gradient of the soil. So for the critical hydraulic gradient, so for zero effective stress, here's the corresponding formula, where the critical hydraulic gradient is equals to the submerged unit weight over the unit weight of water. Okay, this is the submerged unit weight. It's just the difference of saturated unit weight and the unit weight of water. So for most soils, the value of the critical hydraulic gradient ranges from 0.9 to 1.1 with an average of 1. Okay, let's answer this sample problem. Uh, Consider the upward flow of water through a layer of sand in a tank as shown in the figure. For the sand, the following are given. We have a void ratio of 0.52, and the gravity of solids, or the specific gravity of the soil, is 2.67. Calculate the total stress, or water pressure, and effective stress at points A and B. What will be the upward seepage force per unit volume of soil, and calculate the critical hydraulic gradient. So let's solve this. So we have a given specific gravity 2.67 and void ratio 0. And that we can compute the saturated unit weight of soil. So the saturated unit weight of soil is specific gravity plus E over 1 plus E divided by the unit weight of water. So 2.67 plus 0.52 over 1 plus 0.2 multiplied by 9.81 kilonewtons per meter. So that's the saturated unit weight. Saturated unit weight is equals to multiplied by 9.1. It's 20.588 kilonewtons per cubic meter. So have now the saturated unit weight. Uh, the first question is to calculate the total stress for water pressure and effective stress at point A and B. So it's much easier to compute the values at point B first, the bottom, since we already have the difference in pressure head, which is 1.5. So for letter A, um, let me just put the saturated unit weight here, which is 20.58 kilonewtons per meter. So at point B, let's determine the total stress first, which is easier. The total stress is just the sum of the products of unit weight in each layer multiplied by its height. So the first layer here is full of water. This is water. So unit weight of water times H, which is 0.7 plus meters, plus the saturated unit weight of soil multiplied by 2 meters. Okay, so unit weight of water 9.81 kilonewtons per cubic meter, 0.7 meters plus 20.588 kilonewtons per cubic meters and 2 meters. Okay, so 9.81, 0.7 plus 20.588 multiplied by 2, 48.043 kilopascal. That's your total stress. So for the pore water pressure U, so unit weight of water multiplied by the total height 0.7 and 2. So that's a total of 2.7 meters, and add the pressure difference, which is 1.5 pressure head difference. Okay, so 9.81 kilonewtons per cubic meters multiplied by this 2.7 plus 1.5, that's 4.2 meters. So for water pressure is 4.2 times 9.81, 41.202 kilo Pascal. That's your water pressure. So uh, if the total pressure is effective stress plus pore water pressure, so the effective stress is the difference of total stress minus the pore water pressure. So effective stress therefore is equals to 48.043 kilopascal minus 41.202 kilopascal. Okay, so Subtracting the two, we have 8.043, 41.202, 6.841, 6.841. It's in kilopascal also. Okay, so at point A, at point A, so computing the total stress, point A. So point A is 1 meter below the top surface of the soil. So the total pressure is unit weight of water times 0.7 plus saturated unit weight multiplied by the depth, which is 1 meter. So that's 9.81 kilonewtons per cubic meter times 0.7 meters plus saturated unit weight 20.588 kilonewtons per cubic meters multiplied by the depth 1 meter. So the total stress is 1 plus 20.588 times 1. Okay, that's 27.455 kilopascal. So that's your total stress. For the pore water pressure, so the pore water pressure is equals to unit weight of water multiplied by 0.7 again, and we will add 1, and the additional height is, if we will put a piezometer here, okay, so what's the equivalent solution for that? That's h over h2, if we can recall, times z. So that h here is 1.5, or the total difference in pressure head from top to bottom of the surface of the soil. So 0.1 meters plus 1 meter plus, that's 1.5. So h2 here is the total depth of soil, which is 2 meters, multiplied by z, or the depth of soil, which is 1 meter. Okay, so we can now compute the pore water pressure. So the pore water pressure is simply V multiply 9.81 by 0.7 plus 1 plus 1.5 over 2 multiplied by 1. Okay, so that's the total pore water pressure, 24.0345, that's in kilopascal. So therefore, the effective stress is total stress minus pore water pressure. So the pore water pressure is equals to 27.455 kilopascal minus 24.0345 kilopascal. So effective stress is 27.455 minus 24.0345, 3.4205. That's in kilopascal. Okay, that's your answer for letter A. So here are the stresses. For letter B, what is the upward seepage force per unit volume of soil? So question for letter B. What is the upward seepage force. So the upward seepage force is H over H2 times unit weight of water. So H here is the pressure difference, which is 1.5. Okay, the total pressure difference from top to bottom of the soil, divided by H2, the total depth of soil, 2 meters. Then unit weight of water, 9.81 kilonewtons per cubic meter. So that's your F. So let's compute this. We have 1.5 over 2 times 9.81. So 7.3575 kilonewtons per cubic meter. So that's the seepage force per unit volume. Okay. Letter C. Calculate the critical hydraulic gradient. For letter C, critical hydraulic gradient is, okay, ICR is equals to the submerged unit weight over unit weight of water. It's also called as the buoyant unit weight. So that is saturated unit weight minus unit weight of water over unit weight of water. So we have 20.55 kilonewtons per cubic meter minus 9.81 kilonewtons per cubic meter over 9.81 kilonewtons per cubic meter. So that's your critical hydraulic gradient. So the critical hydraulic gradient is 20.588 minus 9.81 over 9.81. So that's 1.099. Okay, that's unitless. That's the final answer. Okay, so that's how you solve uh, saturate stresses on a saturated soil with seepage. So if it is a downward seepage, just change the sign to negative for that additional pore water pressure right here. Okay, so that ends our lecture. Thank you for watching. God bless.